as I mentioned, the fluorescence it can be a very powerful technique to monitor various things. I will show you one more the value of these fluorescence probes. Okay, so if you take a molecule in a solvent, the solvent will be surrounding this molecule. So when you excite this molecule, it will go up somewhere and the solvation around that molecule will change. Suppose you take a carbonyl compound. In the carbonyl compound, if you have in the ground state, it is going to be like this, minus and plus. When you excite this, it will go to the excited state. Where the polarity might change, it will become more negatively carbon, this one it could shift completely. When it does shift completely, that means the solvent that is surrounding this molecule, it has to readjust itself and then change its solvation. So you can monitor that, how long does it take, how the molecule, these are very interesting phenomenon. For example, if you have a molecule and you have all these things that are probably the water molecule surrounding this carbonyl oxygen, oxygen was negatively charged, and when you excite it, in 10 power minus 15 seconds, the oxygen becomes positively charged. That means all water molecules around that thing, they are not very happy. They just have to readjust itself. And you can find out how long does it take for this to readjust. So it could be, it cannot happen in 10 power minus 15. It can be minus 12 or minus 3 or minus 5 or all this stuff. How do you monitor with the help of fluorescence is what we call as solvation dynamics. Okay, so I'll show you what happens. So this is basically what is solvation. Solvation means if you put a molecule in a solvent, that molecule is surrounded by the solvent in a particular way. It is not random. This is you take a molecule like this. The solvent is, these are all solvent molecules, and then when you excite it, it gets polarized into plus and minus. As soon as you excite it, the solvent structure is going to be like the same as was before. But what will happen is the solvents will slowly readjust to this minus charge, and then it is going to go like this side is going to go like that. But it is not long, that is going to stay only for a fraction of this time, because this molecule is going to go back to that one. So it is going to be, you can watch how long this solvent molecules takes to reorient itself around this probe molecule. You have to watch by looking at the fluorescence spectrum. Okay. So for example, as you go from here to here, you can see what is happening is it is random. Now it has become highly organized. Okay. So this is the same picture. This is the ground state, and then in the excited state, now with the molecule in the ground state, it has its own solvation because it has got plus and minus oriented in a particular way. Now, if you excite it, it goes here, and then it will immediately start coming down. But what will happen is, as you see here, in the excited state, the solvent, as it starts reorganizing around the molecule, the energy gets lowered. So now, what happens? If you record the emission as soon as you go back. So if you record the emission with the time, the emission is going to be from here to here. Okay. But now, if this molecule is stabilized by the solvent, the energy will decrease. As the energy is decreasing, as you see in this picture, see now, as it decreases, the emission is going to come from various places, from here, and all this. So now you can see, if you record the emission with the time, the emission spectrum will change. That tells you something about how long does the molecule takes to stabilize this solvent molecules. This is the time resolved solvation structure. Okay. Now, if you record this emission, with the time, Now the emission at the beginning is here. After some time, it is not a longer wavelength. Even after some more time, it is an even longer wavelength. So the emission will keep changing with the time. The same emission, and then it will keep slowly moving. You can watch that happens. That time it takes, it tells you how long for a molecule in a solvent to move around. That moving around, this is basically you are monitoring the dynamics of the molecule. How long does it, for example, if you have water molecule in the solvent, how long does it take to rotate? It will take 10 to the minus 9 or minus 10 seconds. But you cannot directly look at your water and see whether it is rotating. But if you have something else, keep it here, and then when it is rotating, the energy of this will keep changing, and then when you record the emission, big things will happen. So this is the basis, and then as you see here, the lifetime will also change. Okay, now, you take for example the coumarin molecules. The coumarin molecules, like what we said before, the emission maximum, like in the case of IDE is I1 by I3, some other molecules, the emission maximum will change depending on the polarity. So basically what happens is, if we excite this molecule in solution, 1, 2 and 3, in for example number 1 is ethyl acetate, number 2 is propylene carbonate, number 3 is methanol. So the solvents maximum are different. Maximum are different because the polarity around the chromophore, which is coumarin, is different in different solvents. Okay. But now, if you take this molecule and then irradiate in some solvent, that polarity will change with time. Because when at the beginning, the polarity is going to look like ethyl acetate. But then after some time, when the ethyl acetate is rotating, the polarity will keep changing. Okay. So you can see here, this molecule, with the time, the emission is shifting. That tells you this molecule is surrounded by water molecules, and those water molecules are rearranging itself around this probe, and that when it rearranges, the polarity is changing. So this is a very useful technique people use. Okay. Now, if you want to find out the viscosity of a solvent, or when you are doing your polymerization reactions, as you have a monomer, and if you polymerize, it becomes a polymer. So the viscosity of this solution is going to get higher and higher and higher with the time. So if you are making a polymer in a company and you want to make a polymer of only this much length, but not this much, when you have a polymer of that length, the viscosity will be different. If it is of this length, it will be very different. So what you do is, you put a little bit of your compound along with the monomer in a big container, and when you start polymerizing, look at the emission spectrum. As you look at the emission spectrum, now if the emission is corresponding to the rotation, viscosity, then at a certain stage you can stop it. So here. So for example, we take this compound. This is the viscosity. The viscosity is measured in centipoise. Okay. So this is 1, 2, 3, 4, 5. And as we see the intensity of this emission, it depends upon whether viscosity is here or viscosity is over here. Depending upon the viscosity, the emission intensity will change for this compound. Some other compounds emission maximum will change. In this particular case, the intensity is changing. As the intensity becomes more and more rigid, then what happens is this emission is getting stronger. Basically, it is a probe molecule. You put the probe inside, for example, this water, and then you add something to polymerize. As the water becomes more and more viscous, the emission of this compound will get stronger and stronger and stronger. At some stage, when it becomes like this number 3, that is what viscosity you want, and then you just turn off the instrument, and then the polymerization will stop. This is how the companies, they make, for example, they make nylon or decaron or whatever, or different particular length, they will use this kind of probe molecules. And here the emission, as you see here, when viscosity is small, emission intensity is less. When viscosity is strong, intensity is high. Can you tell me why the emission intensity depends upon viscosity for this compound. It is not true for every compound. You have to find the right probe. That's where you have to find. People do a lot of different compounds and look for the probe, or they call sensor. I call them as a probe, or I call them as a sensor. Okay, in this case, this is number one. That means the viscosity is like water. And here, this is like viscosity is like a glycerol. Okay, it's a very viscous solution. In a very viscous solution, the intensity is high. When the viscosity is like a water, the intensity is less. But the intensity of the emission maximum does not change. How much light comes out, it changes. Tell me why the emission intensity depends upon the viscosity for this compound. It's not that difficult. Okay. So if you can develop a probe like this, you can sell it and make some money out of this compounds. That's where a lot of interest is there in looking for probes or sensors, things like that. Okay, so why this compound emission intensity is high in a very viscous solvent and is very low, intensity is very small when the viscosity is very low. Why? Okay. No? If you look at this compound, there is a double bond here. Carbon-carbon double bond. This, when you excite it, that is going to rotate. If it rotates very freely, then the emission intensity is going to be weak. It is not going to emit because it is using the energy to rotate. If the intensity, if the viscosity becomes very high, then it cannot rotate. Then what happens if the energy is stuck on the compound? Then it will start emitting as the fluorescence. So in a very viscous solvent, the fluorescence is strong. In a non-viscous solvent, the fluorescence is very weak. It does the same thing like still being we talked about. The only difference is the emission is in a region where you can see. The still being emission is going to be coming in 350, 400, where you cannot really see those emissions. Okay. There are lots of people work what is called as sensors. And there is a journal. There is a journal called molecular sensors or molecular probes and then sensors and actuators and things like that. There are a whole bunch of journals. Because everybody wants to find a way to sense something. Okay. So the sensor, for example, in this particular case, the sensor is going to be a fluorescent molecule. So when it senses something, the emission is going to go down or it is going to go bright very high. So depending upon when you have something, you are sitting here, you put your sensor there, and then you are sitting here, but suddenly it becomes very bright. That means something happened to this water. So depending upon what kind of sensor you put, you can tell, okay, there will be too much sodium there, or too much of the alcohol, or too much of proton or something. So each one is a different sensor. Okay. So how the sensor works is a very simple technique. So this is the fluorescence probe. That is the one that is going to tell you what is happening. And then there is something like a small thing connected to something else. And this is what is called as a receptor that is going to catch the things that you are trying to sense. So as soon as it catches that, and this one, the emission is going to go up or go down. And this receptor is important because that is the one which is going to tell when it is attracting a proton or sodium or some cesium or something, the emission is going to go up or down. Okay, it is not going to be shifting, but it is going to be up or down. Okay, so in this case, for example, if you have a fluorescence probe, this is something you have to look for. You have to this is where the chapter on fluorescence is useful, because you can just look through what kind of fluorescence probe you can develop, because it's always good to have a fluorescence probe which is in the visible field, so that you can see with your eye. And then the other thing is, always better to have a fluorescence probe where the intensity goes up, not that goes down. Okay. So here, there is a spacer, there is something, and then as soon as the proton lands, suppose this is going to be your sensor. This sensor, you drop it in water. Okay, now if you add a proton, that proton will bind to the sensor somewhere here. Now what will happen is the emission of this one either will go up or go down depending upon the mechanism of interaction between this proton and the sensor. Okay. So I'll show you. This is the typical technique that is used. Okay, you take this one. This is the proton sensor. Okay. It's not very obvious what it's going to do. Okay. What it does is, this has got a lot of amines. 1, 2, 3. You know, amines, as I already mentioned 5 times already. Amines has got a lone pair. That means it's a base. If you add an acid and base will react. So this NH, this lone pair will bind to the proton, then it will become NH3 plus. Okay. Now, okay, this is the chemistry. But you have to figure out whether it happened or not. This molecule, looking at it, you cannot tell whether you have a fluorescent sensor or not. Now it is this part of the molecule that is going to tell you whether the proton is there or not. Okay. Now look at this compound. So basically what's going to happen is, if you have this molecule, this is non-fluorescent. If you take this molecule and take a fluorescent spectrum, you will not see anything. If you add acid to the solution, you will see a strong fluorescent. Okay. So if I add an acid to the solution, it will become strong. That means there is a proton in the solution. Okay. Tell me why this is not fluorescent and why this is very strongly fluorescent. So that is a very basic principle by using complex. So you have to figure out, so what is the principle, and then you accordingly adjust the structures. Okay, this molecule is not fluorescent, this molecule is strongly fluorescent. Only difference between here and here is H plus. So if you don't have H plus, this will continue to be no emission. If you add H plus, it will become strong. And that means your solution has got suddenly you have to do acidic. Okay, tell me why this is not fluorescent, why this is strongly fluorescent. Some of you, I think, work with sensors, right? I don't know what kind of sensor. There are a whole bunch of people working on sensors. Why non-fluorescent? Fluorescent. Do you tell or no? You tell it Chinese, whoever is good in Chinese to English, they can translate this. Or you can tell it to everybody in Chinese, so they can figure it out. Whether you tell it right or wrong. Maybe tomorrow should be not sit here. Okay. Anybody else? Anybody knows the answer? Why this one is fluorescent? This compound is not fluorescent. This compound is strongly fluorescent. Okay, it goes back to the lone pair. We talked about nitrogen contains the lone pair. Then it is responsible for the excimer emission and things like that. Okay. Now, if we excite this compound, what will happen is, if they have 2 electrons here, there will be an electron transfer from nitrogen to the anthracene. So it will immediately quench the emission. Suppose you remove that to lone pair, then when you excite it, there is no electron transfer from here to here. If there is no electron transfer, then the compound will emit. So when you excite the molecule anthracene to this one, it can emit normally. But if you have an amine which is willing to donate an electron, that will basically quench the emission. So if you want to stop that thing, somehow you have to tie up the 2 electrons. One approach is just use the proton. Okay, then you can do it. But then the other way of thinking it is just use this phenomenon to figure out that the proton in solution, how acidic, like a pH meter. So you find out the pH of the solution. Okay, so here. So when you excite the thing, what is happening is there's one electron here and one electron here. This orbital is empty. If you have another molecule with 2 electrons, then electron will shift here. Then what will happen is the emission for this will disappear. Okay, you can see here. This molecule is not fluorescent, and this molecule is strongly fluorescent. And this is not a plus, there is no H plus. But this molecule is not fluorescent, but it is used to sense potassium plus. Because if you are in your blood, you want to find out the sodium level, potassium level, some of these things. Because those things are, where they are very important in the context of heart attacks and all this stuff. Okay, so here if you notice, this molecule is attached to this crown ether. It is well known, crown ethers can interact with the small ions like sodium, potassium, rubidium, cesium, all these things. And whether it will attach or whether it will interact, it depends upon the size of this crown ether. So if you want to find out sodium as in the solution, you use a different crown ether. If you want potassium, if you want to have cesium, then you even make it larger crown ether. Crown ether or something similar. Okay. So this compound is not fluorescent, and this compound is fluorescent. So this compound is stuck with the potassium. So as soon as it sees the potassium, the emission comes out. Okay. Tells me why this compound is not fluorescent, whereas this compound is fluorescent. Why? Okay. Why do you think this compound is not fluorescent, whereas this compound is white? Anybody? No? But you are some of you work with the sensor. You work with Dr. BP? No. Do you work with that? Are you a PhD student, master's student, or bachelor student? Master's or bachelor? She's a bachelor or master? Working with Dr. Leaping? Yeah, okay. So, Leaping's lab, they work with some sensors, right? Okay. So, this is a sensor. So, this one is not fluorescent. This one is fluorescent. What is the reason for the difference?
That is the PT.
PET? PET. Okay. So she says this has to do with the PET. PET means photo induced electrons as well. Okay. Basically what happens is, as this molecule in the ground state, this lone pair and this benzene, they will interact. Because this molecule electron orbitals are filled. So in the ground state, you are going to have 2 electrons. When you excite it, this orbital becomes partially empty. Now what happens is, when lone pair electrons will move from here to here, and then the quench is excited. Now, somehow if you can tie up these electrons, which is done in the case of this compound, the potassium plus, it will interact with the lone pair. So then this two electrons are interacting with the potassium, so it is not going to be able to transfer the electron from here to here. If it is not transferring, this molecule is going to become strongly fluorescent. So it can be, for example, it can be H plus, or it can be a sodium plus. But to be able to selectively decide whether you want to have H plus, sodium plus, and all this stuff, now you have to control this part, that is the receptor part. That is, if you have a crown ether which will bind only to sodium, then it becomes sodium sensor. If it binds to cesium, then it becomes a cesium sensor. So for that, you have to change the structure of this part. The emission part is here, but this part is the one which is going to decide whether it becomes a sodium or a proton or cesium or calcium. Okay. So any questions? Okay. So this is a very powerful technique. A lot of people use this because from journals, there is a journal for this kind of sensor. So if you take, for example, this compound, again, if you notice, this is an anthracene. It contains amines. Amines are very useful because when you excite this compound, there is no emission. This lone pair from the amine will quench this stuff. Now, depending upon how you tie up this lone pair, that can become the sensor for that thing. If you use a zinc chloride, the zinc will interact with the lone pair. Now, if the lone pair is tied up, this molecule is going to become very strongly emission, and then it becomes a zinc sensor. Okay, so it is, you can think of this as a whole bunch of things. And there is this molecule. So this part of this thing. Okay, let me just turn off all this. So this is the sensor, and this part is the receptor. If you keep changing these things, you can sense different things. So here this is a phosphate sensitizer and very similar structure. Now the zinc sensitizer, a zinc sensor, and all this stuff. Okay. So this is one way, just to turn it off and turn it on. There are various, you use the features of fluorescence to do the various types of sensing. Here, this compound, now here this is anthracene and another anthracene. These two anthracenes, when they get closer, they form excimer. That's what we talked about in the case of pining. Now, the emission, this is the monomer emission and this is the excimer emission. The ratio of monomer to excimer you can control. So if you can control with some kind of an ion or something, then it can be used as a sensor for the particular ion. Okay. So this compound here, and the guy has used calcium. Okay. So when you have a calcium, when it is, as you start from here, when there is no calcium, you have only the emission from anthracene. When the amount of calcium is increasing, now you see it becomes more of excimer. Okay. So obviously the ratio of this to that, it depends upon the calcium. So tell me why the calcium is able to control this monomer excimer ratio. From the ratio you can tell, okay, how much concentration of the calcium that you have, or some, wherever it is. What is the, these are all very intelligent, cute ways of doing things. It is not like basic discovery where you develop a theory. But here, for example, this guy has used this compound and then used this to show that it can be a calcium sensor. Okay? So how does it do it? You have an answer.
With another correction and exchange the frequency from fluorescence. So you can exchange it from mono oxide.
Okay. So you look at this compound. This has got a lot of single bonds. So see, this one is going to have a lot of different conformations. And no conformation is going to bring two anthracenes closer. So when the two anthracenes are not close, you will see only monomer emission. But if you add, for example, calcium, that calcium will bind to the open crown ether, and when it binds, and what will happen is these two are going to come closer. And see, normally the two anthracenes are like this, and you have this crown, and then when you put this sodium or this calcium, now this one will have to change its conformation, and the conformation, the two anthracenes will get closer, and now this is excimer. Okay. So the fluorescence is extremely useful, and to sense a lot of different things. It can be a polarity, it can be viscosity, or it can be the solvation dynamics, or it can be various ions and all this stuff. So a lot of people they spend their time to try to find out the best sensor possible. Okay? Any questions? Okay. So far we talked mostly about fluorescence. Fluorescence is coming from the excited singlet states. There is also something called phosphorescence. The phosphorescence comes from the triplet state. Okay? So I will spend some time talking about it, and then from there we'll see. Okay, the phosphorescence, the triplet state, the idea of a triplet state and its existence was shown in around 1930s, not long time ago. Maybe the paper came in 1940s. Before that, nobody even agreed there was a triplet. The molecule can exist in triplet state. So this was the original person is D.N. Lewis, and Kasha was a student. So his PhD was on the triplet state. Okay. And there are also several other people, Russians, and these Porter in England. All these people established the concept of triplet states in 1950s and around 1950s. That is about 60 years ago. Okay. Now, the thing is, so basically what will happen is you put a molecule, you know how to take a molecule from ground state to excited singlet state. That is possible. And once it goes there, it will come back down. Then it is called as fluorescence. But taking a molecule from here to the triplet, it is not possible, because that transition is a forbidden transition. That is, this one has the spin of the electrons are singlet, and the spin of the electrons are triplet. You know, the morning I talked about some selection rules for absorption. That is, absorption depends upon electrons, the symmetry and the overlap, and then it depends upon the vibration. The third, it depends upon the spin. If the two spins are the same, you can populate the molecule. That is possible only for singlet. This spin and that spin are the same, whereas here this spin and that spin are not the same. So putting a molecule here by direct excitation is not easy. So when you put the molecule up here, it can cross over to this, and if it does cross to the triplet, then you can see emission from the triplet state. That emission is called as phosphorescence. Okay? So there are two emissions, fluorescence and phosphorescence. And the phosphorescence from here to here, that also requires a change in the spin, like going from here to here, change. So this rate constant is going to be very small. When the rate constant is small, that means this will have a longer lifetime. So the fluorescence excited singlet will have a short lifetime. The excited triplets will have a long lifetime. Sometimes the lifetime can be like a few seconds or even a few minutes. So if you put a molecule in the triplet state, it will take a long time before it emits. Okay. Okay. Tell me, if I record this emission spectrum for some compound, there is going to be emission from fluorescence, emission phosphorescence, and all this stuff. And then it can be for radiative emission, excimer, all kinds of stuff. Assuming there is nothing else except fluorescence and phosphorescence. So the phosphorus, so you will see, when you record something, you will see something like this. How do you know which is fluorescence, which is phosphorescence? Okay, you record emission. Okay. Oh, you want to erase this stuff? I don't know, is it doesn't see an erasable marker or what? So when you see the emission, right? Okay, one more trial. Oh, this one is not even come on. Okay, that's okay. That's good. So when you see an emission spectrum, you are going to get one emission like this, another emission like that. Okay. How do you know which one is fluorescence, which one is phosphorescence? Okay. How do you know which one is fluorescence, which one is phosphorescence? Because, when somebody asks you to take either compound, go and get me the emission spectrum, you record a spectrum, and you talk about DP, is this fluorescence or phosphorescence? You have to tell her. Otherwise, she may not be happy. Okay, tell me, how do you know which one is fluorescence, which one is phosphorescence? Lifetime, that's one thing. You don't know, that is a little bit more complicated. No problem. Huh? You just record the spectrum. So looking at it, you should be able to tell whether it is fluorescence or not.
I think the fluorescence energy is higher than phosphorescence.
Fluorescence energy is what?
Fluorescence energy is higher than the phosphorescence.
Okay. So when you have two emissions, the emission that is at a higher energy is the fluorescence. The emission at a longer wavelength, that is the phosphorescence. Because we said before, between the singlet and the triplet will be a lower energy compared to the singlet for all compounds. There is no exception. So if you have two compounds, you take it from here, put it over here, and then it goes over here and emits, and then it is going to emit from here. This emission will be at a shorter wavelength compared to this emission at a longer wavelength. That is it. So here, for example, this is again pyrene. Pyrene is a good example. You have, this is the absorption. You have an emission here, another emission here. Tell me, which one is the fluorescence, which one is the phosphorescence? There are green and then this one is like blue.
I think the green one is the fluorescence. The blue one is the phosphorescence.
So the green is, if you notice, this is the green and it is very close to the absorption because the absorption, according to the Stokes shift, the absorption and the emission, they will overlap. And then the next one is going to be the phosphorescence. The phosphorescence has the gap. So fluorescence S1 goes to the T1 and then T1 is the next. So if you look at here this picture, so this one molecule goes to the singlet state, and from the singlet it comes to the triplet state. Now from the singlet it will emit from here to here, to the triplet it emits from here. If you look at this arrow is shorter than this arrow. The length of the arrow is the indication of where it is going to come. Okay, so this is the same thing. And benzophenone, for example. In the benzophenone, you see this one is the emission at a longer wavelength. This is the absorption. And this one, the gap is very small. If you go back to here, this one, okay? This is the fluorescence, this is the phosphorescence. If you look at this gap, it is large. And if you go to this compound, the fluorescence is somewhere here and the phosphorescence is here. The fluorescence for this kind of compounds is hard to see because they have a very high rate of intersystem crossing. Going from S1 to T1, the rate is much faster than it can emit from the fluorescence. So there is no fluorescence. So if you look at this, this is supposed to be the singlet and the gap is small. Okay. So tell me, why in this case the gap between the fluorescence and phosphorescence is large. In this case, the gap is very small because this is absorption. The fluorescence, if it is there, is going to be somewhere here. So the gap is much smaller, whereas here the gap is larger. Why?
I think in the below one, the gap between the S1 and the T1, the distance is lower, so the gap is low.
No, yeah. The gap is low here.
Yeah.
Why?
The singlet and the triplet, the energy between there is very low. So
Why? So it is very obvious, the gap between S1 and T1 is small. The gap between T1 and S1 is large. Question is, why for this compound is large, for this compound is small?
Maybe the overlap.
Okay, well, I'll tell you, because you are trying to figure out. If you remember, we talked about, depending upon the character, the electronic configuration of the singlet state, the energy gap between S1 and T1 will change. If it is an N to pi star or pi to pi star. The pi to pi star, the gap is large. When it is N to pi star, the gap is small. Yesterday I showed you a table, like a pyrene, atrazine, all these things are 40 and 50 kilocalories. And when you have a compound like a benzophenone, acetone, and all these are 5 to 10 kilocalories. So, if you look at this compound, oxygen, the main transition is N to pi star. And here everything is pi to pi star. So, pi to pi star, the gap is going to be large, and this one. So, there is one way to figure out what type of transitions you are dealing with, looking at the gap between the singlet and the strip of the fluorescence. Okay. So, if you want to look at the phosphorescence, it is not that easy, because first of all, the phosphorescence is going to, you have to produce the triplet. The triplet is dependent upon the intersystem crossing. If you produce a triplet, it will live for a long time. If something is living around for a longer time, it can interact with everything else around the medium, then it will get quenched and there is no emission. Okay? So, in order to see the phosphorescence, one of the problems with the phosphorescence also is oxygen that is in the solution, it will quench the triplet states. There is a technique, there is a phenomenon called energy transfer. I'll talk about it maybe in a couple of days. So the energy transfer from the triplet of this, if it is lower, energy will transfer to this. Since the oxygen, the triplet energy is very small, like I mentioned to you at the very beginning of the class, 22 kilocalories. So most compounds can be quenched by oxygen. So if you have, like anthracene, you want to see the phosphorescence. You will see fluorescence, but phosphorescence you may not see. Because the phosphorescence will be quenched by the oxygen, and you have to stop that stuff. If you can try to remove oxygen, one way to do this stuff is you use a solvent which becomes a glass. If you cool the solvent, it will become a glass. So once it is glass, then nothing can move in the glass. So even if you have oxygen, it cannot diffuse towards the excited state. So here are the various types of solvent mixture. Some solvent mixture, if you freeze this water, it will become ice. But the ice is not transparent, it is very white. So you cannot pass light through this water. So if you want to do the experiment, the light has to go through the solution. The solution should be very clear. So only some solvents, for example, 2-methyl pentane, it will form a glass which is very clear. When you look at 3-methyl pentane and then freeze it, it looks like a transparent solution. So there are a few solvents which does this. So we usually use these solvents to measure the phosphorescence, not all solvents. You cannot use every solvent that is available in the lab and get the phosphorescence spectrum. So you have to use, for example here, ether, isopentane, ethanol, the mixture is 5:5:2. In that particular ratio, only to form a glass, transparent glass. But you cannot remember all this stuff. These are available in handbooks, so you can just copy, go to the library or somewhere, look at it and then come back and make this one.